All right, good morning. I'm Nils. I'm going to talk about neutron stars in some shape or form. I have no idea what you know, because you've had the privilege of having 1 week, so you know a lot of stuff that I don't know. And I certainly don't know what it is you know that I don't know, which makes this a little bit problematic for me. And therefore, I'm going to assume that you know nothing, right, which is the kind of my starting point. And so I'm going to try to lay some foundations this morning, and then in the tutorial later on, we'll have an opportunity to maybe discuss a little bit more what we actually know, and then we'll see where we end up. And I've got some very able helpers for that will sort me out in case there's something I don't know that you know, and so on. Okay? And so my plan for this morning is I have a set of, I wouldn't call them lecture notes. There's some papers with some stuff on them. Unfortunately, these papers and this stuff uses different conventions and different notations, so they're all over the place. Okay? And my able helpers who were sent a copy of this are well aware of how many mistakes there are in this and so on. So we're going to try to fix this gradually and so on. But the main plan this morning is to lay the foundation for understanding. That's the only slide I have, so I don't really need to change it anymore. Understanding what a neutron star is, and how we go about modeling the different ways that a neutron star can radiate gravitational waves. So I'm just going to leave my schematic of what a neutron star is up there, and you can, when you get bored with looking at me, or if I fall asleep due to jet lag or something, which might happen, you can just admire this beautiful artwork. Okay. But the basic idea this morning is to discuss the ingredients. So what goes into modeling neutron stars and gravitational waves, okay? And so, clearly, we need to understand a bit about gravity, the gravitational waves, and we need to understand a little bit about neutron stars. And so my job that I've given myself this morning is to talk about, first of all, very roughly, how strong the gravitational waves from a neutron star scenarios to be. So it's going to be a back of the envelope exercise. And then remind you of the quadrupole formula in a much simpler fashion than I'm sure Tanja did, because I suspect here is a case where you already know a lot more than I'm going to say. But anyway, because otherwise what I say will be incomplete. And then talk a little bit about what sits in the integrand of the quadrupole formula in general. So how do we describe matter in general relativity in principle, or how do we describe fluids? So I'm going to talk a little bit about relativistic fluid dynamics, but then because the quadrupole formula is a Newtonian type expression, I'm going to sketch how we go from the relativistic fluid equations to the Newtonian case. So I think that will sort of echo a few things that you saw last week about the weak field limit. And then, because I'm sure you will enjoy that part so much, in this afternoon we're going to do this a little bit more detail. And then we're going to talk a little bit more about the equation of state, in particular, what happens when we perturb a system away from equilibrium. And so that brings in some aspects of the neutron star physics, which are kind of and that's where I'm going to talk about this diagram, brings in a few aspects of neutron star physics that on the equation of state that perhaps you didn't need last week. And then we're going to close perhaps, but we might skip that for today, but just by sketching a few elements from gravitational wave data analysis without talking about the foundations in any shape or form, just the key results we need later in the week to understand some of the different statements about how strong or weak a signal is in reality, okay? So that's what I'm planning to do. If you have objections to the plan, you can raise your hand now or leave the room or whatever, but the doors are locked, so you can't get out anyway. And there we are, okay. Okay, so I'm going to start, decide where I'm going to start. I think maybe here is good, because if I start too far up here, then, well, I'll start here, under the light, right? I'm going to try to write big, but the fact that I write big doesn't really help very much, because my handwriting is very poor. So is that big enough? Okay. Okay, so this is the first episode in this. I'm sure if you record this, it will play on YouTube, something for her, and have big clicks. So this is the first episode. You know already what we're trying to do. We're trying to figure out how the gravitational wave contribution to some gravity dynamics works. And so basically that means that we have some metric, which is a solution to the Einstein field equation for some whatever scenario. And in order to identify the waves, what we think about is this is some background, let's call it G mu nu B, plus some little h mu nu. And you know, if you didn't know it before last week, I'm sure it was hammered into you, that what happens is if we solve this in the weak field limit or some small deviations away from whatever this could be, it could be flat metric, which is going to be probably a bit this morning, it could be a Schwarzschild space-time, a neutron star space-time, whatever you like, and then the H satisfies essentially a wave equation. So we have gravitational waves. But what I want to do now is something slightly different. I just want to start estimating how big, in some sense, is this H. Okay? And that's a useful exercise because once we have this estimate, we can start thinking about how can I possibly get a neutron star to create gravitational waves of this amplitude. So what do I need? And I think if you don't understand this, then calculating detailed things in whatever theory of gravity or whatever you do is kind of pointless. Okay? So the way this goes is you start off thinking of the magnitude of this H as something, a scalar, let's just call it little h. Now in general this should be small, but as you probably know, it's not clear what that means. Right? Because if you do into different coordinate systems, different gauges and so on, it's not clear what you're actually comparing here, but let's not worry about that for now. And then what you can do is you can write down in general, which is true for pretty much any radiation, but, first of all, let's just write what we expect this guy to mean. What we expect this H to do is stretch an object a delta L distance, an object of size L, a delta L distance. So this is what we're trying to measure in a detector, and then roughly we would like this number to be something like, we think this number is going to come out to be something like 10 to the minus 21, and that's the kind of estimate that I want to do. I just want to show you where this number sort of comes from and how we relate that to neutron stars, okay? So the estimate I'm going to write down comes from knowing or relating this H to the flux of gravitational waves. So the gravitational wave luminosity or the energy loss of a given system. And basically, this is a result you can write down based on dimensional analysis. You don't need to put in any numbers at all, but I'm going to put in the numerical factors anyway. And you know probably already that if you want to calculate this from a quadrupole formula, it's kind of a messy calculation where you need, products of third time derivatives of the reduced quadrupole moment and blah, 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 and averaging over wavelengths because you cannot a gravitational wave to a point. It's gravity interaction, and therefore you need to sort of compare things and average over wavelengths. Okay, so what the estimate I want, if you do it in full detail with all the C's and the G's, we have a C cubed 16 pi G times the H dot. So there's time derivative of the H, and that's squared to make it the energy I want. And then this guy is equal to 1 over 4 pi squared. So this is just the sphere over which 4 pi d squared. So this is the distance to the source. And this is just simply the area as the system, the waves expand, and then E dot over here. So the energy loss due to gravitational waves goes like H dot squared. Okay? And then there's some numbers we don't need to care about, and then the distance. So if we recast this and say let's cheat, let's say that we lose the energy on some time scale, let's call it tau. We have some total energy and we just lose it on time scale tau. That gives me an idea of E dot. And let's say that H is just a monochromatic signal with some frequency, let's say F. So we get a 2 pi F for the time derivative and then that H. Okay? This is all I need to do. And then plug this in, try to remember or decide first of all what units we're going to use. So we use CGI units, or CGS units or SI units or what units you like. That's, I think, in my experience, which is limited, but the number of times I've made mistakes in this regard are not limited. Putting units into general relativity is probably the hardest thing you ever have to do. And that is because as relativists we're lazy. We set C and G equal to 1, and then we start believing that actually they are equal to 1. And then sometimes an astronomer tells us that actually, sir or madam, these quantities are not equal to 1. You have to put them in, they have values. And you start thinking, what could those values possibly be? And then you try to remember the speed of light in some units. That's difficult. You're laughing now, but in 20 years' time or so, when you get to my 30, 40 years' time, when you get to my venerable age, and you've done this 1,000 times and you made 1,000 mistakes, you won't be laughing anymore. It's a very sad story. Okay, I plug these in, and what comes out is a number which is 5 times 10 to the minus 22. And then scaling these different quantities I want, the energy, to, in this case, a fraction, 10 to the minus 3 of the mass energy of the sun, which is a useful measure in this context, square rooted. I've got tau of 1 millisecond, also square rooted, but 1 over that, because I got E over T, tau. I've got the frequency scaled to a kilohertz, to the inverse power, and then finally the distance, 15 megaparsecs, also inverse. Yeah. So that was a lot of writing. It took up the whole board, which means the lecture is probably because I have no space left. Okay? So this comes out of this exercise. So what do I learn from this? Well, I learned that I have, first of all, why did I use this number? 15 megaparsecs. I used 15 megaparsecs because that's an estimate of the distance to the Virgo supercluster. So that's the cluster of galaxies. And basically, if you work out any typical thing that happens in the neutron star's life, say it's born, you probably know from last week that in our galaxy we see supernova explosion, say once every 30 years or something like that, give or take. That means that if you build a gravitational wave detector to look for gravitational waves from supernovae, and all you can see is our galaxy, you have to wait a long time, much longer than it will take you to finish, say, your PhD thesis on observing gravitational waves from supernovae. Therefore, you need to look further out. And so if you look to the Virgo supercluster where you have many galaxies, then these events will happen, say, several times a year, and you might be lucky. And so that's why typically we use this kind of number. Some people have 15 or 10 or 20 or whatever, but that's the typical number. Okay? So I don't have much of a choice. Why did I choose a kilohertz? Well, I chose a kilohertz because, you know, the ground-based gravitational wave detectors are sort of have a sweet spot at a few hundred hertz. A few hundred is more difficult to write than 1, and therefore hertz. It will also be a typical number for us for neutron stars latest, so that's fine. Millisecond, well, I'm thinking of something fairly fast, so maybe that's just a number. It matches this one nicely. And then you see that to get this 10 to the minus 22, I need to put a fairly large amount of energy in. Okay, so what I'm saying in this estimate is I'm releasing 0.1% of the mass energy of the sun in a millisecond, right? Now that's a lot of energy in a very short time. So this estimate originally comes from the problem I said, we'll try to estimate supernovae. I can do a little bit better than this, or better in a sense, I can simplify, because this might not be the number I want if I want to think about how detectable is a gravitational wave signal. As we'll see later, this is a small number, but you can improve on this number by clever data analysis tricks. And simplistic, very, very simplistically, I'm insulting anyone that ever did any data analysis by making this statement, but, you know, because I don't work in that field and they don't like me anyway, I can say whatever I like. Okay? So, very simplistically, the effective amplitude that you get after analyzing the signal, let's call it hc, goes roughly as the square root of the number of cycles in the wave you observe times this h. So if we're thinking of, say, a system that just oscillates and we observe it for a certain time, then the number of cycles you're going to get is just the frequency times tau times h. Okay? And now you see why it was immensely clever of me to have a kilohertz here in a millisecond. When I put this factor in, those two just drop out. Okay? And what I'm left with then is an estimate that says that hc is just the 5 times 10 to the minus 22 again, which is lucky, I don't have to change the number. The energy, 10 to the minus 3, square rooted, and the frequency, which I get left, so it's sloppy, 1/2, and the distance, of course, you can't get rid of. Now that got very sloppy because I had to put them down. So this is the final result I want. And what does it tell me? Well, it tells me that if all I want to do is ballpark how strong a gravitational wave signal is from the point of view of observing it, which is weighed in here, all I need to know is how much energy do you release at what frequency. Okay? And therefore, this number, when people start thinking, in order to build a gravitational wave detector, when people started thinking about this, actually when people started thinking about this, clearly there was confusion, but in the 1990s, say, when LIGO was first mooted and designed, this number was the target. Right? And this was the target for a simple reason. You cannot argue this away, right? Of course, we didn't know how much energy you're allowed to release. In many cases, we still don't know. But what we do know is the typical frequency to expect signals from. So you saw stuff from Tanja in Spiral and things last week, I'm sure. But this week, the focus is going to be on neutron stars, and then what you can do is just very simply say, well, the typical frequency you have of these, and this is true for any self-bound system, essentially, if you have mass m and r, the typical frequency you expect is something like the potential energy m over r cubed, okay? We're going to derive a specific case of this probably on Wednesday. Okay, to show that this is not just, I didn't just make this up. And if you put in neutron star numbers, say 1.4 solar masses, 10 kilometers, and you remember the value in whatever these units were, then this comes out as something like 2 kilohertz. Maybe it should be something like that. Okay? And so now we're pretty much where we needed to go for this first bit, the warm-up. We have an idea of how strong the gravitational wave signal would be. Now we know this should be 2, so forget it. Square root of 2, forget about that number. So we need an energy of about 10 to the minus 3 solar masses to be released through whatever mechanism we can think about. Okay? Okay, so now that I've done that, I want to make a list. My daughter is she's a big fan of lists. She started making lists for everything. You're going to go out and buy something, there is a list. Whatever you're going to do, there's a list. She didn't pick that up from me. I'm useless with lists. I usually just wing it. My lists, I've got one item and then I make up the rest as I go along, which is a bad thing. Lists are good, okay? And so I've made a list. Look, here. But I'm going to write it down on the board in a different order because the list I made was just wrong, okay? So I want to make a list, and then as a first exercise for a tutorial, you can make your own list. It could be a shopping list or whatever you want. I'm not going to mark you on whatever list you make. But my list is going to be, okay, let's be imaginative. I'm going to put some things on my list, and then I'll just see if you can come up with some more things I should put on it, okay? But my list is going to be, how could a neutron star possibly radiate gravitational waves? That's my list. Okay? And I'm going to be an optimist, because I like being an optimist. So I'm not going to say, how can a neutron star, how do neutron stars radiate gravity? I'm really, this is how it works, okay? Do. So let's see. And I'm not going to number them. Oh, let's put numbers. Why not? Number 1. The preeminent source of neutron star gravitational waves is not the supernova explosion when they're born. So in the early days of gravitational wave physics, it used to be that people thought the supernova explosion that gives birth to a neutron star should be a supreme source of gravitational waves. And the typical numbers that people put in was that you will radiate maybe 1% or this kind of level of energy in the supernova core collapse when the neutron star is born. And then you work out from this that this would be visible out to this distance. As I said, you will see many of these explosions in the Virgo cluster, so great, let's go looking for these. And then the pesky numerical relativists that do simulations started doing these calculations. They found that the number here is not 10 to the minus 3, it's maybe 10 to the minus 6, maybe 10 to the minus 7, maybe 10 to the minus 8. And suddenly, the promise of seeing neutron star signals from supernova core collapse dropped down this list. Started at number 1, and then like a music chart, it dropped. It was popular for a while, and then now it's quite far down the list. Okay. But if there is a supernova going off in our galaxy, so we make this number a few kiloparsec, then maybe this is back on the list. So let's leave it there. Number 2 on the list, and I think it really has to be there, this is probably number 1 on the list, but on the new list, is binary in spiral. Now, this week you won't hear much about binary in spiral, because I'm sure you learned everything there is to know about effective one-body, binaries, tides, and so on last week. Therefore, I'm not allowed to keep this. Going to leave it on the list, but I'm not going to talk about it. But you also learned that there's a little bit more to this, namely how the fact that the neutron stars are not point particles but extended bodies, and the tidal interaction could imprint on the gravitational wave signal last week, right? Does anyone remember hearing anything about that last week? You remember talking about love? Okay, I'm not going to talk about love. Okay. So is that it? No, that's not it. We're going to talk about tomorrow what happens if the neutron star is not perfectly symmetric. So you can imagine, I don't know if you've seen, there are imaging, some maps of the Earth's gravitational potential. Okay? And it looks like a lumpy potato. It's kind of exciting in a way. And of course we know that the Earth has mountains and stuff. We know that the difference between, say, Mount Everest and the Mariana Trench is quite large in our units. In gravitational potential units, not so large, but that's not one. And so it could be neutron stars have mountains too. So if they do have mountains and they rotate, we have a quadrupole movement and there should be some gravitational waves. So tomorrow we're going to look at that problem. But a neutron star is made of fluid, so that means that it can slosh about. It has different ways it can oscillate and so on. And so one way we can radiate gravitational waves or get the varying quadrupole moment is by having the fluid oscillating. And then, as we will see again later in the week, neutron star has a number of different ways it can oscillate depending on what it is made of. And so this is what I usually work on because there's a very interesting question here. I use an observation at some point in the distant future of these kinds of phenomena and invert it back into what the star is made of. And I'm going to talk a little bit about that problem because I think it's important. And then related to this, and inevitably related to this, as I will explain, is the fact that it's very hard to imagine kicking a neutron star hard enough to get this large an energy. So one way you can do it without kicking, if you like, if you let the neutron star kick itself, by having some system, such that certain fluid oscillations or some fluid dynamics is unstable. If you know anything about fluid dynamics, especially when you couple in things like the electromagnetic field, it is that these systems are notoriously unstable. There are many different instabilities that could come into play. And so the idea then is that if the system is unstable, then maybe the fluid waves will grow large enough that I will get an interesting amount of gravitational waves. Okay? So that sounds easy enough, maybe. We need to understand when this system is stable and when it is not. The problem is, as I will explain again, probably on Thursday, this is an intricate sort of tug of war between instabilities being present and various mechanisms trying to counteract them. And that brings in all sorts of nasty nuclear physics, that much of it we don't know, and so this problem becomes really difficult. Okay, so people would like to add more things to the list. Sorry, the answer to that question should be everybody. You want to add more things to that list. You want to figure out something new, right? You want to win the Nobel Prize. For me, it's too late, right? So you want to add stuff to my list. I'll leave that for you, but that's my list for this morning. There is more, but I think, for example, I could add number 5. Number 5 could be, I have a neutron star. It accretes a little bit of matter, so it gets a little bit more heavier. At some point, the nuclear physics tells me there is a phase transition, so the equation of state changes, so the star contracts a bit. It releases some gravitational potential energy, and therefore it could release gravitational waves. Sorted. Number 5 on my list. I can keep on going. The ideas become more and more harebrained and crazy, but that phase transition thing is not mad, it's just not very promising when you work out the numbers. Okay, so these are the main ones. All right, let's start again. Good morning. Okay, so what I want to do next is I want to, in this list of ingredients that we know, and we need, okay? I want to write down something you know, and something I will need tomorrow. But let's write it down anyway. So let's just remind ourselves of something we know, namely the quadrupole formula. And there are two reasons for writing down the simplest version of this. Tomorrow we'll need it, as I said, because we're going to look at rotating stars. Later on, we'll also need it because we need to contrast, write down to what we need when we look at fluid perturbations. Okay? So that's why I want to write it down in the simplest context. So now what I'm going to do is the very simplest version, and I know, because you got 5 days of lectures from Tanja last week, that you have this in such exquisite detail that I really don't need to write it down. But I feel for me, I have to do it anyway, because otherwise I'm not doing a complete kind of job here. Okay? So I'm going to write this down in the weak field approximation, where I expand with respect to some flat Minkowski metric. So this is my actual approximation. And then you know that the way it goes, I'm skipping all the steps because you are experts and I'm just pretending to know this stuff. That the trick here is that you introduce a trace reversed quantity. So you just take this h and you reverse its trace. And for some reason, that magical trick makes all the difference. It's not a magic trick. The reason it works is simply that when you write down, or works, the reason it's a good idea is that when you write down this guy, let's call it h mu nu bar, so it is h mu nu minus a half mu nu times the trace of h. The reason this is a good idea, in case you never thought about it, is that this combination is exactly the combination of the two-index object, metric, and the trace that sits in the Einstein tensor. Okay? So you could almost see from the beginning, yeah, if I want to introduce something, this would be a good idea. Okay. We do this. We use the game with many names. I'm not going to write them all down because the blackboard is not large enough. But the idea is that you make sure that the divergence, so now because this is flat, I'm going to use partial derivatives, so partial with an index mu. Take the h bar, need to have a mu upstairs, something like that. The divergence of that vanishes. That leads us to the wave equation. And now suddenly it's a 16, and now I'm going to drop the C's and G's, because now I'm going to pretend for a moment that I'm actually a relativist again. And if I keep on writing C's and G's all the time, frankly, there's not enough chalk in this room. That's typically what you get. Although I have cheated, I've kept from the Einstein equations. So let's write them down just to remind ourselves. In general, I've kept the stress energy tensor, I've kept it as T mu nu with the same name, which is really a bad thing to do. Okay? But here, this is only the parts that lead to the gravitational waves. Okay? So if you write down the total stress energy tensor as being a star plus some wiggly bits. This is just the wiggly bit. Okay. Seeing all this, you know that we're clever, we can integrate this. The way to do that is use the retarded Green's function for the wave equation, and we get an expression. And now again, write this down. Now this is only in spatial components, in transverse traceless gauge, which I'm sure you were talked about last week, so I'm going to just cut to the chase. We have now put the numbers back in again, 2g rc to the fourth, and then the reduced quadrupole moment, I with a bar, 2 time derivatives, tt again, because it's transverse traceless, and it's function only of t minus r. Okay. So I'm writing these things down simply because at some point we need to start thinking about what do they mean. You know, what is actually sitting here. So we need to understand, first of all, I've talked about the age, how big it should be. We need to understand that in getting to the wave equation, we made a choice of coordinates. In writing down this expression, we made the statement about reducing the number of degrees of freedom we have left in the problem maximally. So we're working in this transverse traceless gauge. In order to get the simplest, we need to understand that here, because of the time derivatives, the key point is not what the initial and final configuration might be. So for example, neutron star supernova core collapse example of how much energy do you release in an explosion. You can get a hugely optimistic estimate by saying, I start off with a star with this gravitational potential energy, I finish off with a star with this potential energy, and I can release the whole difference as gravitational waves. Okay? So you simply write down energy initial minus energy final equals energy gravitational waves, or something clever like that. And the answer is completely wrong, because it's not where you get to, but how you get there that matters. It's how did the matter accelerate in the process. Okay? So gravitational wave astronomy is a superb example of why the journey is much more important than the destination. Of course, when you travel, that's not necessarily true. You like to arrive at the actual destination, not just have an exciting journey. But in this case, the journey is everything. And then for tomorrow as well, we just need to recall that the way this reduced quadrupole moment is defined is just by taking the quadrupole itself. Sorry, let's do it like this. It's an integral over the density distribution and then the location, not whatever it's position vector, minus a third to remove the trace with the Kronecker delta, and then integrate over a volume. Okay. So right now, I'm going to stop here with this sort of strand of the discussion. What I want to do next is start asking, okay, how do I work out the connection between this T mu nu, the stress energy tensor, and the acceleration down here? How do fluid bodies move? And so, if I want to do any problem that involves neutron stars, ultimately, what I need to do is I need to link whatever my description of the matter is to how it moves through to something like the quadrupole formula. I need time derivatives of the velocities and so on, right? And at the heart of that problem really lies understanding fluid dynamics in full general relativity. Okay? So that's going to have to be my next stop, to talk to you very briefly about how we model fluids. It has to be in general relativity, not because I'm a purist or anything like that, but as I'm sure you were told last week, a neutron star is a general relativistic object. And ultimately, you want to model these objects with, I'm sure Tanja talked about the love number, as I said, and the equation of state. The simple fact is, if you take a Newtonian theory, you take your given equation of state that your nuclear physics colleague gives you, and you plug it into this Newtonian expression, you calculate a star. Okay? What typically happens is, for a given central density, which links to the nuclear physics, you get the radius of the star vastly wrong. I mean, hugely wrong. Okay? And of course, the problem is that Newtonian models don't have a maximum mass. So they don't collapse at a certain given point. So you know already from these very basic statements that we need to understand this problem in general relativity. Okay? But life is not quite that simple, or in fact, that problem can be too hard. And so we also need to understand what the link is between these relativistic systems and simpler Newtonian systems, because this, after all, was a Newtonian type estimate. So what I need to plug in here is a Newtonian kind of result. Okay? And this is how it goes. What we actually do day to day is we often have an idea. Well, actually, quite rarely have an idea. But when we have an idea, we first map it out using a back-of-the-envelope estimate, as I sketched already. Basically, yeah, interesting. If the answer is yes, or perhaps, as long as the answer is not no, it's totally uninteresting, go away. Okay? If the answer that this idea could be interesting, then you try to map it out in a little bit more detail. Okay? The first protocol would be a Newtonian kind of estimate, because Newtonian theory is a little bit easier than relativity in some ways. I'm not allowed to say that because I'm a relativist. And of course, general relativity is the most beautiful of theories. But when it comes to estimating fluid dynamics, etc., it can be a bit of a pest. Okay? Especially if you want to do magnetic fields and other things. And I'm going to come to that shortly. But, and then, if you still believe that this is a good idea, and you want to go to your friend that works in, say, LIGO India, because it's going to take you some years to calculate this, and therefore LIGO India will be in operation, and it will be making detections, and people will be interested in whatever you have to say, then you have to do the calculation in full general relativity, and you have to put in the full detailed physics. Okay? So that's a sort of natural sequence of events, or a natural sequence along which one could or should progress. But I want to make it easier. In a sense, I just want to give you an idea of how I think of relativistic fluids. I'm doing this for two reasons. I think one is to give you that idea, and the second one is to be able to talk a little bit about how the fluid dynamics links in with things regarding the equation of state. And then I'm going to relate back to that diagram, which I haven't talked about yet, and things you probably heard last week. Okay? And I think this is quite important. So, if you go to the textbook, you know that the starting point for any discussion of matter in general relativity is to understand the stress energy, momentum, stress energy, energy stress, momentum, whichever you want. I'm lazy, I just say stress energy tensor. Okay? And you know, probably because I'm sure you've done GR courses, you know that there are only two stress energy tensors that are of any relevance to humankind. Dust, which is used in cosmology, which is collisionless, and the perfect fluid, which is used for everything in general relativity. Okay, so now I'm going to dispel that myth and tell you that those two stress energy tensors are of no relevance to anybody, okay, apart from the people that write textbooks. What do we want? Well, we want to solve this problem that I wrote down and stupidly erased. We want to solve the Einstein field equations, but we really want to know what to put in on the right-hand side. Okay? So what does that mean? That means we're dealing with matter. If we're dealing with vacuum sources, it's easy to know. It's the only case we know what to put in the right-hand side, okay? Because it's 0. And even I can do that. So this problem always starts by introducing an observer. Because in order to explain what there is, we need to decide who measures what. So what we do is we put in an observer, let's say U alpha. Greek indices are 4 dimensions, whichever Greek index I happen to use. So let me give you an example why we need to have this observer. It's a well-known, everyday kind of thing, electromagnetism. You know that the electric field and the magnetic field are defined only once you decide who measures what. A moving electric field leads to a magnetic field and vice versa. So if I measure an electric magnetic field E and a vanishing magnetic field and you move relative to me, you're going to disagree. Okay? And so here's the same. The electromagnetic field obviously go into the stress energy tensor at some point. So unless you tell me who is measuring this, I cannot know how it relates to me. Okay? Now I'm not going to talk about electromagnetism because that would take us too far. But basically what I do is I still need this observer. And then as per usual, I have a world line, how this little box of material flows through space-time. And the U alpha is just a tangent to that world line at any given point. And I measure, naturally associated with this world line, the proper time tau. So this is a curve tracing out in space-time with tau as the parameter. So this is the usual way to do it. So once I have this, I make sure that it's normalized. To 1 or minus c squared, depending on your conventions. And because I normalize it like this, minus 1, sorry, I'm using a minus plus 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 signature. Because of this has to be true. We'll need this shortly. And in terms of the trajectory, U alpha is simply the tangent vector. So in terms of the coordinates in space-time, once I know the coordinates, I can take the proper time derivative, and that gives me this U. So that just tells us what is this observer. So what about the stress energy tensor? But what do I want this guy to observe? What are the material properties? Well, one thing I might want to observe is, say, how much energy is in this box. Okay? Let's say I define an energy density, let's call it epsilon, then that is going to be simply the contraction with this for velocity twice on that stress energy tensor, whatever it is. Okay? So whatever the stress energy tensor is, it has an energy content that I am going to measure. So this is an experiment, if you like. Okay? I have a magic energy meter that I carry with me. I move with the full velocity U alpha, and whatever the matter is, it has a stress energy tensor. When I read off, I know one of the components of this. But I can measure energy, not just energy, I can also measure energy, momentum, flux. Let's call it momentum. So this is now the flux relative to me. So that means it won't have a component along U, because if it had a component along U, I would pick it up here. Okay? So I'm going to define that, say pi alpha. And I'm going to define it simply as this contraction. And I want to make sure, so this is important, that it has no component along U. Right? So I could put the projection in here, making sure that this is orthogonal. Okay? So that means I got one component here, I got three more components here. So now I got 4. This guy is symmetric, he's got more than these 4, so I'm missing 6. So what are those 6 going to be? Well, they could be the stresses. Let's call that pi alpha beta for now. And so I'm going to be lazy, I'm going to put in a projection. So this guy. Minus, plus. So this is just taking the projection orthogonal. So this, if you hit this guy, so if you do alpha beta U beta, then that has no component along U. And therefore what I'm doing here is I'm just taking whatever is left. So the trick goes, define the energy, because you know the time component according to this flow is the energy. Pick up the energy flux or momentum flux relative to this observer, and then whatever is left, just call it stress. And if you feel stress after me writing down this, don't worry, this is messy, okay? So this is a decomposition that goes back to originally Richard Tolman, I think, in his book on relativity. And I don't think we talk about it enough, because what we tend to do is we tend to write down the perfect fluid. So for our purposes, I think this is the simplest option. It's the very simplest option in the relativity textbook, but for what we're doing, this is the simplest. The simplest option is the perfect fluid. And the perfect fluid only has the energy. Oh, let's write it like this. And a pressure. So that's probably not the way you're used to seeing it. Usually one writes it as P plus epsilon U alpha U beta plus P. So he only has 2 scalar parameters. Okay? So now, I'd like to go over here, just for a moment. So last week, you probably learned a fair bit about neutron star interiors and the equation of state. Okay? So what do we know about this strange object? Well, we know that it involves nuclear physics that we cannot test in the laboratory. We know that it involves many different states of matter. Okay? We know that when we start from the surface, we basically have iron. And as we go deeper, we get more and more neutron-rich nuclei. They still freeze to form something we call the crust, which is essentially an elastic distribution. So the nuclei are still in a lattice, but when we get to something called neutron drip, the neutrons start dripping out of the nuclei and form their own sort of neutron gas. We know, or we think we know, that that neutron gas has to be a superfluid. Okay, so now, just by those statements, we see that this is a complicated object. Okay? We have the nuclear lattice with neutron-rich nuclei permeated by a superfluid. Right? This is messy. Okay? But it's about to get worse. When we get to a fraction of the nuclear saturation density, something like a few times 10 to the 14 grams per cubic centimeter, the protons also become unstable in the nuclei. So we have a proton gas and a neutron gas. If the star has a magnetic field, as it will have, because we see these guys as pulsars and so on, so they have to be magnetized, the protons will form a superconductor. So now we have a proton superconductor mixed with a neutron superfluid. These are wonderful words, but I don't think I know what they mean. Okay? And I've worked on this for decades. And it's about to get worse, because the neutron superfluid rotates by forming slim tornadoes that we call vortices, and there's bunches of them in a neutron star, and the superconductor carries the magnetic field, most likely in the form of flux tubes, which is kind of, again, not quite slim tornadoes, but they're very thin, sort of quantized objects carrying the flux. And so we need to understand how these flux tubes interact with the vortices, and how the fact that they live in this odd fluid combination, how that works. Now this is a big, big problem. It's a big, big problem because we don't have any everyday experience of anything like this. We don't have any lab experience of anything like this. And so this is a hugely complicated question. But the main principle is quite simple. This is not a perfect fluid. Okay? It is not a perfect fluid because it has elasticity here, meaning we have to have the stresses. Okay? It has a superfluid, which means that there is a contribution that can flow without friction, meaning it doesn't have to flow along with, this guy that goes against convention and makes up his or her own mind and flows a little bit as it likes. Okay? That means we don't just have one flow, we've got something relative to it, which means that we're wrong. We know that this guy's temperature, it cools, but the heat must flow. Again, there's a relative flow relative to whatever observer you introduce. Okay? Unless you choose an observer that flows with the heat, but then the matter goes somewhere else. And finally, it has a magnetic field. The magnetic field is carried by charge currents. The clue is in the word, currents. Something flows. Okay? And so, this is not a neutron star. We need elasticity, we need superfluids, we need heat flow, and we need charge currents. At the very least. This is a very, very important list, because this tells you that everything you learned last week about that love number and so on might not be quite right. So what you would have to do is ask yourself, are these things important? And then decide. And so, for example, you can ask, does the fact that I have an elastic part of this star make a difference? The answer for the love number is no. It's less than a 1% correction to what Tanja told you last week. Okay? But nevertheless, okay? So, disregarding this fact, so contradicting myself in the finest tradition of teaching, let's have a look at the fluid dynamics. 20 says 27 minutes, so that should be enough. I want to look at the textbook version again. This is not my favorite way of doing it, but I want to have to do it this way because you might connect better with it. Of relativistic fluid dynamics. I'm going to sketch the problem. I'm going to talk a little bit about the connection to the equation of state. And that's going to be important because it's going to allow us to make connection over here again. Okay? And then, given time, which I'm not sure we'll have, we'll talk a little bit about how we get to Newtonian physics out of it. So that one I might be short, because I was thinking in the tutorial this afternoon, that was going to be one thing we're going to also look at. How does that calculation go? Okay, so we can, if I don't have time now, we can sketch it on the board and discuss that in the afternoon. That's fine, because that's more of a calculation, okay? So the point of this exercise is to find out how do fluids move. And basically, I want to write down relativistic version of the Euler equations for fluid dynamics. Okay? And so the way this goes in the textbooks is that if you take the Einstein tensor, let's do it with alphas and betas again, then you know that by definition this is divergence free. It's constructed in such a way that it has no divergence. And therefore you know that the stress energy tensor, whatever it is, has to be divergence free. Because it sits in the right hand side, so if you kill the divergence on the left hand side of the Einstein equations, the right hand side has to go. And now what people do is they do a very clever counting. Okay? They count the degrees of freedom they would have here if they put in the perfect fluid. Okay? And they see that there are 4 equations here, and the fluid problem has 4 degrees of freedom. Has an energy, a velocity, with a relative velocity with 3 components, plus the pressure, but you also, so that's 5, but you also have the equation of state. So now you're down to 4. You need 4 equations. And look, magically, there are 4 equations here. Therefore, this has to be the relativistic equations for fluid dynamics. Okay? Now, before I write down those equations, let me just tell you that this logic is completely wrong. Okay? It's only true if you take this to be a perfect fluid. If you put in something like heat flow, so an extra piece here, then you got more variables and you don't have enough equations anymore. So you will not get like the heat equation out of this construction. And so you need more. But let's forget about that for a moment, because we want to start from the beginning. Okay? So let's take this as given, but just have a caveat in our minds. So what we need is take the perfect fluid and put it in this expression. So I'm going to take the whole thing. Work it out, right? So, but I'm going to do it after thinking a little bit first. So out of this first term, I'm just going to pull out the u beta. So I'm going to write this as u beta times grad alpha of the whole thing. And then, obviously, what I didn't take the derivative, what I took the derivative of times the u beta, because I didn't take the derivative of that yet, so it just gives me this. And then the other term, well, the g is compatible with the covariant derivative, so that just goes through. That derivative is 0, so I can just write this as, say, grad beta upstairs of p. So that has to be true. Has to be true barring possible typos and other mistakes that I probably made. Okay. So then, this is still an equation with, this is the whole thing, but let's isolate one component. Let's multiply this thing with u beta downstairs. Okay? The first term, u beta hitting this, is just u beta contracted with itself, is -1. Right? The second term, u beta here, that becomes the u beta derivative u beta, that was 0. The third term, well, it's just going to be something. So what does this give me? Well, it gives me minus is a divergence of some flow plus u beta grad beta of the pressure, and that has to vanish. So we're going to do two things. We're going to just plug this back into here. Okay? I can just say, take this construction here, that's exactly what sits there. Right? And that means that whatever sits here is just minus this construction with the pressure derivative. Put that in. Then I have two u's. I need to be careful with the indices so I don't have a beta and a beta, but that's everyday work. Then I get the whole thing. And what happens is, I plug that in, and what comes out is simply that P plus epsilon U alpha grad alpha of U beta upstairs, say, is minus that pesky projection. I don't want to spend time on this expression because it comes out easily. P. Yeah. So this is just saying that a fluid, because it has pressure, does not move on geodesics. Because if this was a geodesic, this would be zero. Okay, so this is essentially the acceleration is due to pressure gradients. Okay? I'm going to come back to that in a sec. But where I want to spend a little bit more time is not on that expression, but on this one. Okay? Because you see, if we take this equation and we expand it out a little bit more than I have done here, one more step, then I'm going to get a U alpha. Let's take the U alpha. Then I get a minus U alpha gradient alpha acting on P plus epsilon. I gotta go to plus U beta grad beta P here. So the pressure is going to drop out from that piece. Okay? And that means that here I really only have a derivative of the epsilon. So this is really an equation for energy conservation along the flow. So that equation looks like U alpha grad on epsilon, which comes from this term. And then the piece that is left, which is the divergence of U itself, because I took out U. So that's going to have plus, I think, yes, a P plus epsilon of grad alpha U alpha. So this is important. And one thing we're going to do in the tutorial is look at how this leads us back to the continuity equation for fluid dynamics, that nothing is created or destroyed. Okay? But now I want to do something slightly different. I want to do something dirty. I want to do some thermodynamics. Because when you do fluid dynamics, an equation of state, etc., one thing you have to juggle with all the time is thermodynamics. So I'm going to do a basic one-component thermodynamic exercise. And it's going to turn out to be, I think, quite useful. I hope. If it's not useful, it's almost coffee break time, so we can just take it or leave it. Okay? So the way the exercise goes is I have something called the first law. But I've integrated it. And once I integrate it, it simply says that P plus epsilon is the number of particles times a magic quantity called the chemical potential mu. I have for many, many years had a love-hate relationship with the chemical potential. I like it, but I hate it because so many of my colleagues say to me, but what is it? And then I struggle. So let me explain to you why I like it and why you should like it too. And if you don't like it, then you're in trouble, okay, with me. You might not care about that, and frankly, it's not that important. So what is the chemical potential? Well, the chemical potential says that if I have the energy of a system, in this case the epsilon, and I change the number of particles in that system, then the chemical potential tells me how much the energy changes if I do that. Okay? Of course, here I only have one kind of particle, so this really should be a straight derivative. Later on in the exercise, in a couple of minutes, the last dying moments of this lecture, so this is a definition, but this kind of thing is not just true for variations, it's also true for derivatives. And so this means that actually it's also true that grad of epsilon is equal to mu grad n, because this is a variation. I can do that in space, or I can do that in, configuration space, or whatever you like. Okay, so this is always true. So now I can use these two. You can see I can replace this guy here with this. And then I can replace this guy here with n mu. Okay? And then you see that both of these terms will have a factor of mu, this one here and this one here. And then you'll see that this guy is just the derivative of n, and this guy times u, and this is n times derivative of u. So what comes out is this. So this says that something like the particle flux is conserved. And if you did this exercise from a fundamental particle point of view, you would start with this. Remember, I told you that this way of thinking of fluid dynamics is backwards. Okay? And this is the reason. The natural way to start is here, say, I've got a particle, let's call him N for Nils, because that's obviously the perfect name for a particle. Hasn't been discovered by CERN yet, but I'm sure it's coming. Or maybe it's N for neutron, which is maybe better in many ways. This particle is conserved. It's never destroyed or created. Meaning, I know if it flows through space-time with 4 velocity u alpha, this has to be true. Okay? And then I build the fluid dynamics that way, rather than this way. So why is that useful? Well, it's useful because that then allows me to say, well, suppose I don't just have the Nils particle, I got the Bala particle, the Thomas particle, and I've got all your particles as well, okay? As I have here. A neutron is made out of neutrons, protons, electrons, muons, hyperons, quarks, you name it. Okay? Might need to allow for, as I had in my list, some of these guys to move relative to one another. Electrons, protons move relative to one another to give me a charge current. Okay? So if I build the fluid dynamics that way, I can do more. So to close, I think, yeah. Let's just ask, what happens if we take this kind of argument and allow us to have three kinds of particles? Protons, neutrons, protons, electrons. Okay? As a neutron star. And so the aim of this final bit is to connect with something you may or may not have talked about last week, namely Fermi gases. Did you talk about that? Okay, cool. And what I want to do is I want to close the loop on that perfect fluid and get back to basically a statement saying, what are the assumptions, other than there's no charge currents and heat and so on, that allow us to work with perfect fluids, allow everyone that does modeling for gravitational waves using neutron stars to pretend that reality is a perfect fluid? Why do we get away with it? Okay? So that's the question. And we're going to answer that, and then I'll give up. Okay? So let's take matter made out of neutrons, protons, and electrons. Let's assume it's at 0 temperature, which is really a cheat, but let's do that. Wouldn't be difficult to put this in, but I would have to tell you some more stuff. Then, in general, each particle, or species is better, each species has a chemical potential. So, for example, the neutron has some number density Nn. I take the variation of the energy, whatever it is, with respect to this, and I get a chemical potential μn. Okay? I hold all the other number densities fixed to do this. So it's a proper partial derivative, where I think of the number densities as variables of the equation of state. Okay? So this epsilon is the equation of state, whatever it is. Okay? It's not the usual P pressure is equal to density. It's a higher level statement of energy. Okay? And then the thermodynamics says that this P plus epsilon is simply the sum over these guys. So it's symbolically something like this: nx mu x, sum over the x's, and x is n, p, and e. What is this? Let's see. So that's it. This is a more complicated thermodynamic relation, right? Clearly. So let's see, how do we get to something that depends on only one variable? The perfect fluid had P as a function of epsilon or something like 2. So here I want to have really only one variable left over here. How do I get there? Well, the first thing I do is I say it's charge neutral. And I spell neutral correctly. So let's say it's charge neutral. What does that mean? Well, I have to make it charge neutral, because if it's not charge neutral, I could have charge currents, and I don't have that, right? So I need to get rid of that. So I need to make sure that each fluid element has the same number of protons as it has electrons. So that means that Np is equal to Ne. That means I can factorize this out. Let's say we work only with Np, it doesn't matter, kill the other guy. Okay. And then let's change variables, because when in doubt, change variables and see what happens. So I'm going to change to baryon number, let's call it n, which is the sum of neutrons and protons, and proton fraction, which is np over n. Okay? So now I just plug this in. The first thing I do is to pull this np over, or pull this nn over here, and write this, write this as n, big N minus np. Okay? Shunt that over here, the remaining np that I get, combine it with this, and then introduce that xp. So what do I get then? The first term is just n times mu n. And then I have the second term, which looks like this, nxp times mu p plus mu e minus mu n. Okay. So that was a trick. Sorry to pull a trick on you with just a few minutes remaining. It's a bit nasty. So what is the purpose of this trick? Well, the trick is this combination, as you learned last week, vanishes if the matter is in beta equilibrium. That vanishing is the condition for beta equilibrium, the balance of the chemical potentials. Basically saying, if I create a neutron, I have to retain overall energy balance, so I have to destroy a proton and an electron. Okay? So we are done. The only thing that remains in order to make this into the thermodynamic relation I wrote down for the perfect fluid case, right, is to rename this guy and drop this index. Right? This statement says there's only one chemical potential that matters in this problem, and I'm back to the perfect fluid. Okay? So to finish then, what do we learn from this? So let's work this exercise backwards. But let's think about those scenarios for when neutron stars can radiate gravitational waves, and let's ask ourselves, do we think these assumptions are going to be true or not true? Okay? So take a star, I crush it together with another star in a neutron star merger. Is the matter going to stay in beta equilibrium? Yes or no? No. Perfect fluid, out the window. Okay. I was too violent. I'm sorry. Let's be more gentle. Let's take your problem from last week. Let's take the love problem. Okay? We have two stars gently meandering towards one another under the influence of gravitational radiation reaction. They stretch a bit towards each other, or the other departs a little bit due to the tide. Okay? You encode this tidal interaction in the love number. Did you by any chance last week calculate this love number? Yes? So you know that the calculation of the love number assumes that the matter is in beta equilibrium. Okay? It does so because the classic calculation of the tidal interaction is for binaries that go around one another for absolutely ever. Okay? So it's fair to assume that this system settles into an equilibrium and it stays there. Now let me tell you a simple fact. Okay? During the neutron star binary in spiral, say the time it takes from the system entering the LIGO sensitivity band to the final crash. It's about 15 minutes. Okay? During that time, the stars stretch more and more. Okay? The matter is not in equilibrium. And the chemical reactions that want to drive you back to equilibrium act on a timescale of something like a year, several months. So they can't do this job. The matter is not in equilibrium. It can't be a barotrope. We're missing something. Is it important? I don't know. But it's clear already that problem, we're missing something. So the lesson here is this assumption, when you're talking about dynamical systems, systems that evolve, this assumption is very rarely true. Okay? The assumption of charge neutrality is true to some extent, but because we have electromagnetism, if we want to have real neutron stars, we have to have charged currents. So the statement that we're working with perfect fluids is simply not true at a deeper level. But 30 seconds to go on the clock. The reason we do it is because we don't know how to do much better. It's too hard. Okay? So reality is neutron star modeling is a balance between the realism, what you would like to do, as represented kind of by that sketch. You'd like to do everything because you're a megalomaniac. You just want to understand the whole problem. At least I do. And what you can do, and depending on your level of competence, you can do more or less. But my philosophy is we have to do more than the perfect fluid. And at that point, my time is up. Thank you for this morning.